This video is brought to you by mywayteaching.com.
In this part, let us study about propagation of a pulse on a rope. Okay, it is a simple example, or we can say observation. You can easily see the motion of a pulse on a rope. You can also see its reflection from a rigid boundary, and you can measure its velocity of travel. You will need a rope of diameter 1 to 3 centimeter, as they have taken in this case. We need a rope. The diameter is 1 to 3 centimeter. Okay. And 2 hooks and some weights. You can see here 2 hooks and some weights. You can perform this experiment then. Take a long rope or a thick string of diameter 1 to 3 centimeter and tie 2 hooks on opposite walls in a hall or laboratory. As you can see, it is tied to the hooks. Let one end pass on a hook and hang some weight about 1 to 5 kg to it. So this is the weight they have hanged here. The walls may be around 3 to 5 meter apart. And you just take a stick or a rod and strike the rope hard at a point near the one end. You can do that at this point. That creates a pulse on the rope which now travels on it. When you hit it with a rod, that creates a pulse on this rope and it travels on it. Then you can see it reaching the other end and reflecting back from it. So you can also see that once it travels to this end, again it reflects back from this end back to this end again. You can check the phase relation between the incident pulse and the reflected pulse if you want. You can easily watch 2 or 3 reflections before pulse dies out. And you can take a stopwatch and find the time for the pulse to travel the distance between the walls. And you can measure its velocity, compare it with that which we obtained the equation for that before, that is V is equal to square root of T by mu. This is also what happens with a thin metallic string of a musical instrument. There also you can observe the motion of a pulse, isn't it? The major difference is that the velocity on a string is fairly high because of low mass per unit length as compared to that on a thick rope. The low velocity on a rope allows us to watch the motion and make measurements beautifully. In case of that musical instruments, that density mu will be very low so that we get a high velocity and even we can observe it with more vibrations, or we can see that movement very fastly because of its velocity. Okay. Now let us study another important concept, that is nothing but speed of a longitudinal wave, speed of sound. Okay. Speed of a longitudinal wave, that is nothing but speed of sound. See, in a longitudinal wave, the constituents of the medium oscillate forward and backward in the direction of propagation of the wave. And we have already seen that the sound waves travel in the form of compressions and rarefactions, isn't it, of small volume elements of air. And the elastic property that determines the stress under compressional strain is the bulk modulus of the medium, and we know already what is that bulk modulus is. So that bulk modulus is given by the equation B is equal to minus of delta P by delta V by V. Okay, and here the change in pressure delta P produces a volumetric strain, that is delta V by V, and this bulk modulus has the same dimension as pressure and given in SI units in terms of Pascal. The inertial property relevant for the propagation of wave in the mass density rho with the dimensions m L raised to minus 3. Okay, and the quantity B by rho has the relevant dimension, that is B has the dimension m L raised to minus 1 T raised to minus 2 and rho m L raised to minus 3. So this is the dimension of B by rho. Thus, if B and rho are considered to be the only relevant physical quantities, then we can write the velocity expression is equal to C B by rho. Okay. Again here C is the undetermined constant from dimensional analysis, and the exact derivation shows that the value of C is equal to 1. So in that case the general formula for longitudinal waves in a medium is given by B square root of B by rho. Okay. For a linear medium like solid bar, the lateral expansion of the bar is negligible and we may consider it to be the under only longitudinal strain. That expansion we can neglect it completely. So in that case, that modulus of elasticity, Young's modulus, which has the same dimension as the bulk modulus, dimensional analysis for this case is the same as before, and it yields the equation that we have written here, that is C square root of B by rho. And the speed of a longitudinal waves in a solid bar, if you derive that, we get an equation speed of longitudinal waves in case of solid bar. We can write it as y by rho, where this y is Young's modulus. Okay, and in this table you can see speed of sound in some of the media. In air it is 331 meter per second. In air at 20 degrees Celsius temperature it is 343 meter per second. In helium it is 965, hydrogen and water it is 1402, it's very high, and water at 20 degrees Celsius it is 1482. seawater. In solids it's even higher, like in aluminium it is 6420. Copper, steel, granite, rubber, they have given all the values. Vulcanized rubber, everything. So from this table, one thing is clear, that liquids and solids generally have higher speeds of sound when compared to gases, isn't it? Why this so? This happens because there are much more difficult to compress than gases, and so have much higher values of bulk modulus. This factor more than compensates for their higher densities than gases. You can density of these things will be higher, right, compared to gases. We can estimate the speed of sound in a gas in an ideal gas approximation. For an ideal gas, the pressure P, volume V, and the temperature T are related by the equation that we already studied. PV is equal to N gas equation. Okay, here in this N gives the number of molecules in volume V, and Kb is nothing but a constant which we call it as Boltzmann constant. Okay, and T is the temperature of the gas. And this temperature is always expressed in Kelvin. So for an isothermal change, it follows from this equation A, that is V delta P plus P delta V is equal to 0. Or in other words, we can write minus of delta P by delta V by V is equal to P. Okay. So in this equation, if you substitute in the equation that we studied before, if you substitute B is equal to P, we can do, we'll get this equation. Okay, and the speed of the longitudinal wave in an ideal gas is given by V is equal to square root of P by rho. Here we have substituted B is equal to P, and this relation is first given by Newton. So only we call this as Newton's formula. Okay, in the early equation we had B is equal to minus P delta V by V. But later in this particular equation we have substituted in this equation the value that we just got, that is minus delta P by delta V by V is equal to P, isn't it? So in this equation if you substitute the value of P, we get B is equal to P. Okay.